Okay, 11.8 begins on page 648. And our discussion today is about spheres, both how much it takes to cover it and how much it takes to fill it. Spheres mean balls, softballs, volleyballs, basketballs, stuff like that. We're going to cover them like you cover a baseball in skin and stitch it up, right? Or filling it either full of air or sand or whatever. We're talking about how much space is inside of it. I have taught this lecture before, and I've tried to show people where these formulas actually come from. I get the impression when I've done that they wish I hadn't and just given them the formulas. So the formula?
Yeah.
Yes.
Please.
Sure. Yes, please.
I'll keep track of them right over here. Surface area of a sphere is 4 pi r squared. That's it. Volume of a sphere of a sphere, we all know we're talking about roundy shaped things, is 4/3 pi r cubed. Now, even though it's kind of hard to imagine with the roundy shaped things we're talking about here, whenever you are talking about area, whenever you're talking about area, you're talking about 2 dimensions. And look, 4 is a constant and pi is a constant. R is used twice. That's your 2 dimensions. 2 variables. They just happen to be the same thing. Whenever you're talking about volumes, there will be 3 variables. They just all have to be the same thing here. Okay? Now, just a brief note about this, just real quick. I'm not going to tell you where it comes from. I'm just going to tell you how to try to imagine it. Do you remember we talked about if you slice a sphere like an orange? Remember we talked about that if you pull them apart and look at the cross sections, and if you slice it through the middle, you get the biggest possible circle that you're looking at. And it's called a great circle.
Yeah.
Okay? So, if you took a sphere and sliced it like that, then the the area of one of those circular faces would be pi r squared. The radius of the sphere, pi r squared.
Yeah.
So what we're saying here is, if you could take an orange or something that you sliced and stamp it out 3 or 4 times and cut them out carefully and really went nicky-picky on it, it would cover the sphere exactly. 4 of those great circles would cover it. Okay? Without any overlap, and cover the whole thing. This guy right here, the reason why there's a third, when we've run into a third before this in this whole process of going through this chapter, it was always when something came to a point. Well, there's no pointy things on a sphere, so why are we dividing by 3? There is a reason. And it takes a little imagination, but have any of you, I don't know if this is going to help you imagine this or not, but have any of you ever eaten a pineapple? They slice it, they slice the skin off of it, and then you go and you reach into one of the things, you pop that one out. Have you ever done that? Some of you have, some of you haven't. If you go in and reach right around one of the little husky things, that's left, if you don't slice it all the way, if you don't slice it too deeply, go into those little husky things. If you go right and wrap right around the center of that with something like a melon ball or something, you can reach in there and pop out that piece of pineapple. It's really sweet, really nice. It leaves the core out. Have you ever seen that? So what I'm asking you to imagine is if you took a sphere, a ball, and you reached in with something until you reached into the center and you closed it in, so it went in like this so that it would be a point, and you pop that out, you would have a pyramid because all the pyramids on the surface of it would stick into the center. Do you see what I'm saying? And it gets smaller as you go to the middle because you got less circle to grab onto. All I'm saying is if you reached in there and popped one of those out, it would be a pyramid. That's why the third. Because all a sphere is clear to the center for all of its volume is all of those pyramids that reach a point as they go in. They're all over the sphere. If you pop one of those out, that's where the third comes from. Because it's a bunch of pyramids that you add together, believe it or not. Or cones if you pull out roundy ones. But still, cones have the 1/3 in. So I know I wish I had a better demonstration for that, but can you imagine what I'm saying? It comes to a point as you pop that out of there, and that's the reason for the third. I don't know if that'll help you remember it or not, but it's 4/3 pi r cubed. So now you have the tools. Let's go see what they're going to ask us to do with it. Example 1 says, find the surface area of the sphere. And they're pointing right at the radius. And the radius is all you need. So you square the radius, which is 64. Take that times 4, which is 256. And multiply that by pi, 256 pi. You do it on your calculator. Square inches, because it was area. You got to be able to put the correct unit on it. Are you with me? And the next one though, this one's not so easy. The next one tells you what the circumference is of the circle. It does not just hand you the radius. So what we have here is a sphere. It's hard to draw a sphere on, that look kind of spherical? And what they've told us is that if we were to put the circumference on this all the way around like that, that circumference, they're pointing to that is
12 pi.
12 pi. Okay, so the circumference equals 12 pi. I can't find the surface area unless I can discover what the radius is. But the circumference of this sphere goes right around the middle, which means that this is a great circle. If I find its radius, I'll have the radius of my sphere. Well, circumference, if you'll recall, is 2 pi r. And I know what circumference is. It's 12 pi. So if I divide 12 pi by 2 pi, I get 6. Because the pi's cancel. 12 divided by 2 is 6. You clear on that? Now I have discovered my radius using a previously known formula. Now that I know the radius, I find the surface area by writing 4 pi times 36, which is 144. And that's in whatever units it is. I didn't observe that. Is it feet?
Feet.
Okay. So it'll be in square feet because it's area. But we had to go discover our own radius. It's the only variable we need is radius, but they didn't give it to us. So we had to go find it using a previously learned formula. You with me there? All right, moving on. Look at example 2. It says find the diameter of the sphere. And all they give us is surface area is 20.25 pi. So here's our deal. We got a sphere. And they tell us that it takes to wrap it up, takes 12.25 pi is the surface area. And they want to know what's the diameter. Well, if I knew the radius, the diameter is easy, right?
20. Yeah.
So we say the surface area is equal to this. Well, the surface area, okay, let me write it down. Surface area is equal to 4 pi r squared. And I know this surface area is 12.25 pi.
The surface area.
What?
The surface area is 20.25, not 12.
Oh, I thought it was 12. Thank you. All right, let me go back to what I was trying to say with the wrong number. Surface area is 20.25 pi. So here's my formula. I replace the surface area with 20.25 pi, and it equals 4 pi r squared. So the pi's will divide out. If I divide both sides by pi, they're gone. That's awesome. When you can get rid of an irrational number. Then I got to take 20.25 and divide it by 4. Now square root. So you square root that to get an r. 2.25 equals r. And so the diameter is what? 4.5, twice that. And that answer is in just plain old units. So what did they tell us the units were on this for the volume? Inches?
Centimeters.
Oh, centimeters. So this is just centimeters because it's just a length. So choose the correct unit. They're not always going to be the same. It's not always going to either be square units or cubic units. This one's single. Everybody okay so far? All right. So we just use the formula, and whatever they give us, we solve for what they don't give us. All right. Let's see what they've got going for the next part. On the page, we got a little discussion about volume, but we're not going to go through it. We're just going to take this on faith, and it works. It's been working for eons, so probably true. And they give you that core concept in the middle of page 650 that the volume is 4/3 pi r cubed. So in example 3, again, they just hand us the radius. This is a soccer ball, and it's got a 4.5 inch radius. And they want to know the volume of the soccer ball in cubic inches. So we take the volume formula, and I suggest you write it down every single time you need it so that by the time you're done, you'll have it memorized. And then you plug in what you know, which is the radius. Is that right? Do you all know how to cube things on your calculator?
Yeah.
Everybody, is there anybody who does not know how to make their calculator cube something? Because we've been squaring things a long time and there's a dedicated key for that. But if you have to cube something, different calculators do it different ways. Is there anybody who does not know how? Okay, with their calculator. You got a TI. Anybody that has a TI of any kind, somewhere right here near the navigate, well, right in here, there's a thing that looks like this little, it's called a caret key. And you just stick that in front of the 3. So the syntax on this would be parenthesis 4 divided by 3 pi, and then you would put in the, I'm sorry, I shouldn't be doing it under there. It's over here, my mistake. To do this one, it would be 4/3 pi times, and then you would type 4.5 and then hit that caret key and it'll have this little hat up there like that. And then you just type a 3. Hit enter. That's how you cube it. Okay. Is there anybody else who doesn't know? Because sometimes it's not a little caret like this. It's a y to the x key. Anybody got that? And if so, do you know how to use it?
Yeah.
Everybody good? Okay. So make sure your calculators know how to cube things, because this is the first time we've had to cube anything in this. It's always been squared things. Okay, so you just crank that out. You leave the pi hanging out till the end, and you get, oh no, they did, well, it's 121.5 pi, or 381.7. That seems, you guys all know about the size of a soccer ball, right? You've had some experience with soccer balls.
Yeah.
I'm assuming that this is about right. It's about 9 inches through, 4.5 for radius. What we've just discovered is that you can put 382, almost 382 little kid, you know, when the little kids, when they play with blocks, they've got letters and numbers on the outsides of them.
Yeah.
That's about a cubic inch. 382 of those will fit in a soccer ball if you saw them up and stuff it in the corners and stuff like that. You know what I mean? Volume always surprises people. It's amazing because they go, I had no idea it would hold that much. Volume is always a surprising thing for most folks. Okay, next. Example 4 says, they tell us what the surface area is, and they want us to find the volume. Oh boy. The surface area of a sphere is 324 pi. So this is what we get, surface area, 324 pi, and we are supposed to find the volume. And the volume equals 4/3 pi. I'm going to need something to cube, and they didn't hand it to me. I'm going to have to get it out of there. Surface area, remember, if we've got surface area, is equal to 4 pi r squared. So if we solve this equation for r, we can put it here. Yes?
Yeah.
All right. So I'm going to divide the pi's out again. 324 divided by 4 is 81 equals r squared. If we square root 81, we get 9. So 9 goes here. And we'll have to cube 9, which is 729. Well, anyway, this is what your calculator would do. This is how you figure it out. Would be times 9 raised to a caret key to the 3, and then just slap a pi on the end, or multiply by pi and give you the total. It doesn't really matter. They got it both ways in both cases. So we had to first solve for r, and then use that r in a volume equation, and you get 972 pi. You should punch it out in your calculator to make sure you're able to get that. And if you don't want to do it, if you want to work the pi into it, it's 3,053.63. Cubic centimeters, that's a lot. A cubic centimeter, by the way, to give you an idea of what that is, it's slightly smaller than a dice that you roll in the game. Cubic centimeter, a little bit smaller than that. Cubic inch is like one of those little kids' blocks. Give you some idea, feel for how big they are. Okay, wow, only one more example. It says, finding the volume of a composite seems like the last 2 or 3 sections. So we're going to take 2 shapes and put them together, and we got to find the volume, the whole volume. So, in example 5, it says, find the volume of this composite solid. Now, you're looking at that. Can you even tell what they're trying to do to you there? They gave you a short cylinder, like a little bit taller than a tuna fish can, more like a canned chicken, like that. And they get it, it's just exactly the right height to scoop out half a sphere. And they want to know what's left. So if you had a solid block of wood, and some way or another you had a drill that could drill right down into the top of it and cut out and remove exactly half of a sphere, We want to know what remains. Can you see that's what's, in example 5, can you see that's kind of what they're after?
Yeah.
Notice that the dotted line, which is the bottom of the sphere, just hits the center of the bottom of the can. Okay? So the height of the can, think about this with me. The height of the can is the radius of the sphere.
Yeah.
Okay. So this is our strategy. With the composites, this is how we handle it. What we've got is a cylinder, the area of a cylinder. No, not area, we're on volume now. The volume of a cylinder minus half the volume of a sphere. Because that's what we're going to scoop out of it. Are you with me or not?
Yeah.
You understand this original strategy? You okay with it? Now we put in formulas. Volume of the cylinder is pi r squared h. Formula here with the 1/2 is because we're doing a hemisphere, but the volume of the sphere part of it that goes in here is 4/3 pi r cubed. And it's the same r for the can as it is for the sphere, and the height of the can is a radius. We talked about that.
Yeah.
Have I lost anybody there? Because I need to describe it or draw a picture and show you why that is. The height of the can is the radius of the sphere. And the radius of the sphere is also the radius of the can. So this is something we haven't done before. There's an r squared there, but it's times another r. Because the height is a radius. Have I lost anybody?
No.
Kind of, you maybe not come up with it yourself, but you understand what I'm doing here?
Yep.
Minus 1/2 times 4/3 is 2/3 pi r cubed. Multiplying this times this would be 4/6, which is 2/3. Do you see that?
Don't you or what's it called, FOIL it into the other numbers?
No, you don't, because that would, if you had plus signs in between there or minus signs, you would.
Oh,
But if they're all together, it's just this times this times this times this. So if I do this times this, I've got a result, and I want to take that result times the others. You know what I'm saying?
Yeah.
You sure?
yes. You just
Okay.
take the one
Anybody
out.
else have a question so far? Now here's what's really cool. I've got 1 pi r cubed minus 2/3 of a pi r cubed, which is 1/3 of those. You don't have to do it the way I'm doing it. I'm just trying to get you to recognize some things. I've got 1 whole pi r cubed minus 2/3 of pi r cubed leaves me with 1/3 of that pi r cubed. Does that make sense? Yeah? Now, did they give us any indication what the radius of any of this stuff is? 2? That's easy. 1/3 pi times 2 cubed, that's 8. So I have 1/3 pi times 8. Since that's a fraction times a whole number, that would be 8/3 pi. Cubic units. What are the units in?
Inches.
Inches. Now, you don't have to do it that way. You do have to get this far. And then you can just start throwing things in there. You can put 2 in for that, 2 in for that, 2 in for that, and make your calculator crank that out. But I just wanted to show you that in this particular case, the R and the height were the same, which means I really have one of these, one whole thing of here minus 2/3 of those things is 1/3. The algebra sometimes shakes out really nicely. Anyway, did you follow all that? That's a composite. I know it doesn't seem like a composite shape because generally a composite is where we take something solid and we add something more to it that's a different solid. This one actually removed it. And so our strategy was a subtraction rather than an addition this time. Okay?
Yep.
All right. Good luck. Make sure you get these memorized before test time because you don't get a cheat sheet. So I want you to do numbers 3, 5, 11, 12, 13 through 17, odd, that's only 3 questions. And I also want you to do number 13 on page 673. That's in a whole nother chapter, but it has to do with this.
673.
Yes, so number 13 on page 673. It has to do with geometric probability. I'm gonna let you hit it cold. We'll discuss it tomorrow after you've had a chance to think about it. But that is not very many questions. 1, 2, 3, 4, 5, 6, 7, 8. Less than yesterday. So get after it. Do what you can with it. Let me know if you need any help.